Hey guys, welcome back. This is, I don't know how manyth video in a row about Tektronix products, but I promise I'm not sponsored by them yet. Um, Today is a special day because I have something that I'm pretty sure almost none of you have ever seen. It's a piece of equipment from the late 80s, early 90s, something like that, meant for very fancy research, like lasers, nuclear particle physics, stuff like that. And it was, at the time, the fastest analog with very important parentheses or asterisks, inverted commas, wherever you want to call it, um, analog tube scope. And it still remains, I think, the fastest one the tech ever made. There was technically a faster real-time scope based on what I'm gonna show you, but it was rebranded by Tech from a company in France, I think called Intertechnique. It was the Tektronix 7250, I think. I'm not entirely sure. I'm gonna correct it here if I'm wrong. So what is it? Well, I'm gonna show you in a second, but first of all, let's discuss about acquiring fast pulses or fast signals. So normally what you would have done to get a very fast rise time was either use the fastest scope that you had available, the 7104 I mean, or if that wasn't enough and your signal was repetitive, you could have used one of these. I know they look like regular Tektronix plugins, but they're actually fast sampling plugins. So this one on the left is the 7S11 and this is the 7T11. They're mating, so they have to be sat next to each other in a 7000 series mainframe in order to use them. And I'm gonna do a video about these and sampling scopes in general in the future, but this is not the point of the video. So you can get very high rise times with these. This is 75 picoseconds or less rise time, but only if you have a repeating signal. So for a single shot event, you're out of luck. You can't use these. These rely on acquiring a signal at various points in time, provided the signal stays sort of constant, acquiring it at various points in time and reconstructing the waveform out of basically points. So this is analog sampling, basically. Your second option was the 7104, as I said, which was a gigahertz of bandwidth, but that might not have been fast enough. So what Tektronix came up with, I think they came up with, was the scan converter tube. And here's an excerpt out of the device's operator manual. And we have a little look at what's inside the heart of the instrument. Basically it's a vacuum tube that has two different parts. So one of them is a very fast right gun, which is basically like an oscilloscope tube, basically. And the other one is sort of like a Vidicon. I think Tech named these Nuicons because they weren't reading off of a photocathode, they were reading off of a diode matrix. So how this thing works basically is that you have a very fast CRT scope tube here that blasts a target area made out of about 1 million diodes per square centimeter, and they look like this. It's an N-type substrate with P-type islands. So the right gun scans the signal across the surface here. And from the other side, once the acquisition is done, once a signal has been captured, there's a read gun that scans across that matrix in a zigzag pattern and measures the beam current. Now, the beam current is gonna be higher or lower depending on whether the target has illuminated the area or not. So this is a way of acquiring very fast signals with not very fast hardware, because the scan of this takes quite a lot of time. The write bit is very, very fast, as the whole purpose of the device is. It's very, very fast, but you read it off slowly. So this is a fast in, slow out. And without further ado, because I've already teased it a while back, this is the SCD5000. Now, the SCD5000 is a transient waveform recorder, and its initial sales price was about 80 grand. So when I looked through the tech catalogs on TechWiki, the first one that had a price for it was about 80 grand without any options. A couple of interesting options were, and I'm going to show you some of them, because spoiler alert, I had two of these SCD5000s. One of them is a trigger, internal trigger, which lowers the bandwidth to a paltry 3.5 gigahertz from 5 gigahertz, because it has a delay line and trigger pickoff circuit and other stuff like that. And the other option is a fast centroider. So basically, in order to get a nicer looking signal, the computer inside has to interpolate and actually do basically just an interpolation to reconstruct the original waveform from the data collected from the matrix here. Okay, let me bring out the scan converter tube itself and we can have a look at that in just a second. So, it's pretty long. I don't think it's going to fit in frame entirely, but here it is. So, up to here, basically, is the right gun. This entire portion is the right gun, and this entire portion here is the read gun. This is the Vidicon or Newicon or whatever Tektronix called it. There was a yoke over here, so the deflection was electromagnetic. And this side here is the CRT scope itself. So what we have is much like the 519. We have SMA connectors leading straight into the distributed element deflection area, deflection plate here. So this is the vertical and this is the horizontal. This is basically the sweep. And we have the cathode filament inside, focusing grids and stuff like that. So pretty bog standard CRT scope when you consider it, but impressive to think that this runs at 5 gigahertz. An interesting thing is that you can see that it's a straight through thing. So the distributed element deflection is basically in line with the input, and the output here had a 20 dB attenuator and 50 ohm termination on the end. I'll try and dig it up, but no promises. Other than that, it's pretty bog standard. The target is that shiny bit there. So that is the diode array that gets erased and then written by the scan converter, and then written by read by the Newicon. And this psychedelic shape here is, I think, the anode acceleration something structure that concentrates and gives you a tightly focused electron beam to read the diode array as cleanly as possible. What's the story of this one? Well, the first SCD5000 that I got off of eBay with the help of a very dear friend, this is completely dead. So the SCD5000 had a broken power supply. It's this beast over here, and it's a enormously complicated power supply. It has lots of fail-safes and stuff like that, and it's the same power supply as in the 1100 series of scopes. Might do a video about it because it's a very interesting switching power supply. It's a current mode controlled switching supply, and it's got all sorts of protections. So every rail is protected against over voltage and over current. And in case you're not seeing any shunts, the shunts are traces of the PCB on the inner layers. It's crazy, and it's very, very nicely designed. So, as I was saying, this thing had a bum tube. So this tube is unfortunately dead. Either the cathode is completely dead on the CRT side or in the Vidicon side, or the target is blasted, because at 100% beam current, the device couldn't acquire any reading whatsoever. I verified the high voltage power supply and it works, so it's not this. Okay, let me bring out some more stuff and we'll go through how this thing operated. So we've gone through the power supply. I kind of showed you that. It's got a lot of power rails, but apparently not enough, because the thing needs more rails. So give me a second and I'll bring out some more power supply stuff. Okay, so what we have here, apologies, all the electrons are going to fall out, is after the power supply, this was the first thing that the power supply interfaced with. This is the regulator board, regulator assembly, and it's basically just a bunch of linear power supplies on a board with some filtering capacitors, nothing important, nothing exciting. Then we have the high voltage bit for the right gun. So this is a transformer, a multiplier, and the socket that mounts on the Vidicon, on the CRT, on the scan converter. And very impressive. This weighs a lot, so this brick is quite substantial. There's quite a lot of filtering or diodes, capacitors, a Cockcroft-Walton multiplier, something like that in there, because you need a very stable power supply for an oscilloscope high voltage. So yeah. And transformer looks relatively familiar to the one in the 460 series, 400 series, basically the newer ones. I'm not entirely sure. It might be, with the addition of this beefier winding. This is obviously for the filament on the scan converter, so isolated floating filament, all that jazz. And remarkably few connections to the base of the tube, as you'd expect it. There's a lot more that's done in the actual tube itself, further away from the first few terminals. And last but not least, just so you can understand how many power supply rails this thing had, so this board takes the 15 volts, the positive 15 volts here, and converts it to plus 365, negative 30, 130, and positive 130. I am assuming that these are for the horizontal deflection and probably something along the lines of, the new icon or something like that. Okay, by the way, these are all perfectly functional boards, and they're good spares for the SCD5000, which I promise I'm not doing this to tease you or anything. I am going to show you all inside, and I am going to do some experiments with it because it's super cool, but I'm just trying to build up to it and to show you just how much effort went into this thing. Remember, an $80,000 device meant for nuclear physics, particle physics, basically stuff like that. This is the 519 of its era. So let me bring some more stuff out and we'll discuss. Okay, so this is the horizontal board, or actually the right gun board. This is the time-based IC out of the 2467B. So they reused quite a lot of stuff in here, and you can see a lot of output stage to drive those deflection plates in the scan converter tube. By the way, this is called, I think, the T750. So the scan converter tube T750. If you're wondering, I'm gonna put links to the entire thing, everything I could find about it in the description. So this is just a very precise time base and very fast as well, because you need to sweep at very high speeds to get any reasonable information out of a very fast pulse. And interestingly enough, here there's an AD581JH, which is a 10-volt precision reference. It probably has something to do with the precision of the time base, because this is an integrator. Inside there's an integrator, and it probably relies on a precise voltage in order to get an accurate and linear sweep ramp. So this is the horizontal, the right gun. This is for the read gun, I think. Read gun assembly, yeah. So this is all the video amplifiers for the this bit here is the scan control, so the output amplifiers for the scan. You can see these are the terminals that went to the scanning. These are DACs, which I'm assuming are generating the raster pattern for the scan. And there's some other stuff here which is related to biasing the tube, so the read gun basically. These are DAC 08s, by the way. So yeah, my assumption is that these are generating the rasters for the X and Y scan, and these amplifiers and circuits around here, along with these transistors, generate the deflection currents for the scanning yoke. So, by the way, there's no schematics for this entire thing anywhere. Believe me, I looked. The only way I could find the power supply schematics to repair the first one was somebody in the tech scopes group remembered that the power supplies are identical to the ones in the 1100 series of analog scopes. So this is the read gun, and this is basically the video preamp out of the so this basically measures the beam current out of the new Icon. And we're now gonna get into first the trigger board, which is this. The trigger board, insane construction. So A6, Tektronix A6, these are HypeCon, and HypeCon refers to hybrid PCB connections. So you take off these 4 screws, and there's a very fine interface between the package of the ASIC and the PCB substrate. Very, very good for high frequency response. A bunch of transistors which have no idea what they do. Absolutely no clue what this board does, apart from the fact that it does the trigger. And as I said, or didn't say rather, the first SCD5000 that I had didn't have the trigger, internal trigger. So it needed an external trigger in order to trigger. The one that I got subsequently does have the internal trigger, and because of that, it has a bit lower bandwidth. The delay line to the scan converter tube and the trigger pickoff kind of limit the bandwidth a bit to just 3.5 gigahertz. So you can see just how beautiful this board is, and just insane. Okay, next board that I have here is the main processor board. So 68K Motorola with a lot of ROMs. These are the Dallas time bombs that always run out of juice. And a lot of, this is the GPIB controller, you know, all sorts of glue logic and stuff like that, 20 megahertz precision, crystal oscillator there. Yeah, very nice, dense board, very, very dense board. Okay, remember I said that doing the centroiding stuff is very processor heavy? Well, a regular SCD5000 would do it with the 68K on here. You could purchase an option for the instrument, which was this. This is the option 1P, I think. This is the centroid. It's a DSP5600, also from Motorola, which does the floating point math and computation required to get the centroids much faster. So instead of 1 waveform update per second, you might get 7 with this. And you can see here it says DSP centroid cage board. A lot of stuff around here on this board as well. So a DSP, and it's a pretty beefy DSP. It's as I said, a 5601, and all it does is the floating point math for the interpolation, for the centrating algorithm. Okay, let's get a move on, because it's already 20 minutes and you haven't even seen the thing. And we have two more boards here. One of them is control, so I think this board just does control stuff for the... It helps the CPU, digital interface to the rest of the instrument and stuff like that. And this is RAM. This is the memory acquisition. So you don't need very fast memory for this thing. And it only has 1024 points of maximum acquisition window. So you only kind of need a 1K point of RAM, but the vertical resolution is much bigger than a regular digital scope these days. It's 11 bits. So your 1K has to be 11 bits wide per word in order to get all that information. So I think these are 29C983. I have no idea what these are. AMD devices. These are obviously some sort of RAMs. And yeah, anyway, I didn't spend too much time digging in through these, because I was trying to get the thing working and the digital bits seemed to work. So yeah, okay, so this is basically it. A lot of boards. Apologies for the way I'm treating them, but they're gonna be fine, trust me. And this is ESD safe. Okay, let me move the camera and show you the thing, because it's pretty impressive. Okay, so here it is. Apologies for the horrendous flicker or for the lack of you know, power-up shots. It's got the most reflective and fingerprinty screen I've ever seen in a device. So yeah, this was obviously not meant for, you know, day-to-day use, or like a desktop device or something. This was meant to be stuck in a rack. It has rack ears on either side, and it was just meant to acquire data at, you know, at some government or research facility or something like that. So it's not flickering as bad for my eyes. It's not flickering at all, but I think I just nailed the combination of frame rate and shutter speed and scan frequency of this, or the CCFL, because there's a CCFL inside backlighting the LCD. So what we can see is a very rudimentary user interface. There's basically nothing on here apart from a time base, which is the time window, which is selected now. This goes from 5 nanoseconds, I think, as the lowest, to 100 microseconds, and you can see it's not a speed demon by any stretch of the imagination. The trigger is so far behind or in front of whatever it is, because it's gone right now. But if we go back to as fast as it'll go, which is 5 nanoseconds, we'll see the pulse. And if I turn off the thing here, you'll see that when it acquires again, there won't be anything to trigger on. So it's got a lot of measurements you can do. So rise time, fall time, slew rate, proximal, distal, and mesial level, which I have no idea what they mean. I've never seen these nomenclatures ever. Period, frequency, area of the pulse, pulse width, etc. So let's do, out of curiosity, an area, and you have to enter. And so area is 9.179 nanovolt seconds. Yeah, sounds about right. I have no idea. It has no vertical sensitivity. The SCD5000 has. It has the same basically input channel as one of the channels of 7104, and the same vertical amplifier and stuff like that. So 1 gigahertz of bandwidth, same digitizer concept. It's got very little in the sense of trigger, so it's just got a trigger edge, either falling or rising, either internal or external trigger, which is one of these connectors here. And it's got a calibration output, and it comes as standard with N connectors, so none of that BNC or whatever. You can get an option to have this, you could, long gone, long obsolete. You could get an option with to have it with SMA connectors instead of N connections. I think that was the 1F option, whatever. And this was last calibrated in 2003, which is remarkably recent for such a device. It was also fully Tektronix refurbished about at the same time, new CRT, brand new, mostly everything, including the Dallas time bombs in here are fresh, so there's slightly less chance of them dying. And yeah, it's a fascinating device. It's insane that it works. It's the fastest thing I have in my apartment right now. And you can see that basically the pulsar has 2 rise times almost. So there's a faster one here, and then it settles out into here. The fall time is oftentimes faster than the rise time. And as I've confirmed in the previous video with the Tektronix MSO4 series, yeah, the 1.2-ish gigahertz that I saw was the limit of this thing here, not the scope. So this kind of agrees at with the rise time measurement with my 3104. Yeah, it's insane, absolutely insane. And the fact that it works, I've never seen one working, displaying anything, not even on TechWiki. And yeah. Oh, and the 7250 that I talked about, this one's 66 pounds. The 7250 is 140 or something. It's almost 80 kilos. This is 30 and it's back breaking already. The 7250 is almost 80, I think. The 7250 is apparently Tektronix's biggest, heaviest monoblock oscilloscope they've ever made. So it kind of dwarfs the 556 that I have. And it would dwarf many other of their test equipment, so crazy. So let me try and set up a TDR, and we'll have a short chat about that. I'll be right back. Okay, so I didn't have any useful combinations of, you know, connectors and adapters and stuff like that to get anything close to resembling a nice looking peak. If I take off this, I think this is the main culprit. This is a rather poor quality BNC-T because I don't have a BNC to BNC adapter like this, female at both ends, like this one. This seems to be the major culprit, so it knackers the shape of the pulse. But it will still work. What I have here is the cable that went from the input to the scan converter tube, and this is 2 nanoseconds long. So in particle physics usually, and in research and stuff like that, and in RF as well, I think cables are specified by their length in propagation time. So this is a 2 nanosecond cable, which is about half a meter long because it's 4 nanoseconds per meter. But the TDR will show us the to and fro time, so the round trip time. So we should be looking at around 4 nanosecond return trip time. So if I connect this here, we should be looking from leading edge to leading edge, and I hope I can kind of put it like here. And if we add some cursors, let me turn them on actually. What the hell is going on? Oh. Oops. What am I doing? Oh, I'm still modifying the offset, I think. As I said, it's not a speed demon. Whoops. I don't know how anybody could have used one of these daily without just programming it. So let's look at something different. So we have 10 nanoseconds across the screen. So this is this acquisition is the entire window. So we have 1 nanosecond per division. So if we look from here to here, it's about 1, 2, 3, 4, 5. It's not actually 5, it's maybe 4.5 nanoseconds. So it's pretty darn close with the extra length of this cable here and stuff like that. So yeah, it works as a TDR. The pulse is a bit shorter, and that's because of attenuation, but it's also because of some impedance mismatching and the you know, the adapters and stuff like that. Theoretically, this pulse would have been the same height as the incident pulse, basically, almost at the same height, because there's no lost energy when the pulse hits the open end of the cable. Now, I'm gonna get something convenient to short out the end of the wire. I'm gonna do it on camera, hopefully. I'm gonna use another SMA to short out the SMA. And I hope we're gonna see that the pulse inverts, because the impedance now at the end of the cable is 0 and the reflection comes back as inverted. This is really cool. This is the way you establish whether a cable is open, shorted, or has an impedance mismatch. And yeah, this is all down to Thomson's equations, or the equations of the transmission line. So transmission line equations, used to do them in university. I don't remember them very fondly, but again, this is their real life application. So if I had a cable that was half a mile long, well, I don't think I could have had enough memory to see it with this, or resolution or whatever. But if I had a cable that was 10 meters long, then I could have seen it. Let's actually look for a longer cable and connect it instead of this, and maybe increase the length of the interval between the two pulses. Apologies, this is all very impromptu. And I think we're gonna need a longer time window, which is left. So 50 nanoseconds, and let me just delay the trigger a bit, because oh, I don't think it can do that. So our pulse, the incident pulse, is behind. I think I need to lower the trigger level a bit, or increase it rather, so it sees the first pulse and triggers on that one, because now I think it's triggering on the second pulse. I'm not entirely sure. I think this cable is too long. Anyway, it's very, very interesting anyway. So this cable is too long. Let's go back to... Oh, so now it triggers on that one. And if I connect a different cable of a different-ish length, this should be also kind of the same as the first one. Oops. Again, nowhere near a speed demon. So this is about the same length as the first one that we had. And let me look for a different one, a differenter one. Maybe this one will work. I'm just pulling cables out of thin air now. I think this one's too long again. Yeah. Wait a second. I'm gonna try and find an adequately sized cable for a longer round trip time. Okay, so Soviet cable finally pulled through, and this is about twice as long as the other one. and you can see that the time window between them, the time between the pulses is kind of doubled almost. And if I short it out, if I can short it out again, maybe, yeah, you can see that it went negative again. So that's basically it. Again, as I said, this thing was meant for lasers and stuff like that. And you can see now that I removed that troublesome adapter, that the pulse kind of looks a bit better, and actually the rise time is a bit better, so probably some extra inductance and stuff like that in the trace kind of evened it out and made it behave a bit better. Let me just move the pulse itself a bit lower, so I think it's this way. Yeah, it's everything is kind of backwards. I have no idea why they made it so convoluted to operate. I think it's a joke that some Tektronix engineer tried to play on some poor unsuspecting physicist or something like that. So there's always been sort of a rivalry in particle physics between the electronics engineers and the physicists, or at least that's the way it's been in the places I've been, where there's been particle physics and electronics engineers. But yeah, so roundabout, I don't know, it's the same rise time, a bit different, maybe. Anyway, okay, I know that you all want to see inside this one, and that's what I'm going to try and do next. Again, it's a beast of an instrument. It's very big, and I'll have to figure out a way to show you inside and do it justice, because it's, yeah, again, very interesting device. I'll be right back. Okay, this video is getting long enough, so I'm gonna try and speed through a bit this area. So what we have is the input comes from around here somewhere. It goes through this cable and it feeds into this bit here, which is the trigger pickoff. One cable comes out and goes to the trigger board here, and the other one continues into a rigid coax, which is this copper tubing, which is the delay line. The delay line then terminates into here, into another very fancy cable like this one, which is also a bit of delay line if you think about it, and goes into the vertical deflection plates of the scan converter. Underneath here and here are the two boards that I showed you earlier. Here's the horizontal board, the right gun board, and this is the read gun board. This is the video level amplifier. So basically this is the beam current from the read gun. And here's all the digital boards, the trigger board, power supply, regulator underneath there, and that's about it. Behind here in the back, actually right here in the back, there's the high voltage board, and there's another board in here, which is the power supply, the power converter that I showed you that generated 300 and something volts and plus net minus 130. Those voltages are, for sure, now that I think about it more, they're the deflection plate for the horizontal sweep. So that's what they're doing. And if you're wondering, yes, this readout unit can be decapitated and you can take it off. Actually, the one that came with this one was broken. The backlight in it is completely dead, so I used the one from the other one that I had. And yeah, these two bits here, so this trigger pickoff and this delay line, are option 1P, which is the external trigger. If you want to get one of these for yourself, first of all, why? And second of all, make sure it has the internal trigger option, because you can always bypass it and get a full 5 gigahertz of bandwidth if you desire it. But if you don't, you're gonna get a more usable instrument which has an internal trigger. And the scan converter sits inside of here, sort of like this. So about like this. You can see it takes up all of the length of the instrument, so it's a crazy piece of kit. So I'm gonna leave you with this. And yeah, I'm still doing so many things at the same time. I'm working on project balcony kern, which is steadily turning into living room kern. It's right around in there. I'm gonna show you a small picture of it. Yeah, I was just so much stuff going on at the same time as always, and yeah, I'm glad I found the time and I was able to show you this piece of kit because it's not something most people are gonna see ever. This was relegated for the you know the privileged few who worked for the right time in the right place on the right stuff. So, and it's a shame because these are true works of art. This is beautiful from everywhere you look at it. It's absolutely gorgeous. A very, very fantastic piece of equipment. Okay, I think that's enough. If you want more stuff about this thing, let me know. I might revisit it in the future. It's fully working, and I intend to keep it that way. Um, I have basically everything as a spare available for it. So, and I'm doing my best not to kill it, as you've seen. The output went through an attenuator into the thing, so protecting it as much as I possibly can and treating it as gently as I can, so I can enjoy it for a very long time from now on. All right, thanks for watching. Have a great day. See you next time. Bye.